Molecular definitions. There's actually 3 different definitions of acids and bases. The Arrhenius definition, named after Svante Arrhenius, who was a Swedish chemist, is this one. An acid is a substance that produces hydrogen ions in aqueous solution. So whatever the substance is, if you put it in water and it produces hydrogen ions, it's an acid. And that goes along well with the definition of acids we used when we learned nomenclature. Here's HCl. HCl is actually a covalent compound. It's hydrogen and chlorine covalently bonded together. But we learned to name it as an acid. But we also said these are acids if they are in aqueous solution. When you put HCl, which is a covalent compound, into water, it ionizes and forms hydrogen ions and chloride ions. So this is the equation that shows what's happening there. This is not an ionic compound, but it forms ions in water. And so that's the definition of an acid, an Arrhenius acid. Now, hydrogen ions are highly reactive. What is in a hydrogen atom? How many protons, how many neutrons, how many electrons? 1 proton and 1 electron. And the most common isotope of hydrogen actually doesn't have any neutrons at all. So a hydrogen atom is 1 proton and 1 electron. A hydrogen ion, H+, you've taken away the electron. What's left? Just the proton. So basically you have a naked nucleus, a proton. That's not going to be real stable. It's going to react with pretty much anything it comes in contact with. So here we are in an aqueous solution, and we've made these very reactive hydrogen ions. They're not going to hang around by themselves. What's going to happen is this hydrogen ion is going to run into a water molecule, because these are all over the place in the aqueous solution. And this water molecule is going to share one of its lone pairs with this poor little hydrogen ion, this proton, and it's going to form this ion right here. This is H3O+, and the name of it is hydronium ion. The way I think of it is a hydrogen ion is a little tiny thing, right? It's just a proton. It is like a 3-month-old baby. It's too small to be out in the world by itself, right? And so it will always be riding piggyback on something else. In the HCl, it was with the chlorine. You put it into water, the chlorine separates from this hydrogen ion, and it can't just be sitting on the sidewalk by itself. Somebody's going to pick it up. So the water molecules pick it up. Hydrogen ions are never found alone. So this is what is really occurring in an aqueous solution. But we get a little tired of writing H3O+ and having to put water in on the other side of the equation. So we will often refer to it as H+ aqueous. This is exactly the same as H3O+ aqueous. It's just that we're understanding that the H2O is there. Okay? So we use these interchangeably, and unfortunately that's sometimes confusing to students, and I'll just apologize for that in advance. Sorry. Life is confusing. Any questions? When we write the molecular formula for an acid, we generally write the ionizable hydrogen first. This is the formula for formic acid, and that's not one that you need to know, but this is the formula for formic acid. It actually has 2 hydrogen ions, but only one of them, not hydrogen ions, 2 hydrogen atoms, but only one of them will come off when it's put into solution. So here's how these are connected. And I think we made something similar to this in our molecular modeling lab. The carbon has a double bond to one oxygen, a single bond to this oxygen. This oxygen has a single bond to this hydrogen, and the carbon has a single bond to that hydrogen. This hydrogen is not going to go anywhere. It's the hydrogen and the oxygen that's going to come off when you put formic acid into water. It's an acid, you put it in water, it releases a hydrogen ion. This is the one that it releases. So when we write the formula for acids, we write the ionizable hydrogen first, Any other hydrogens get tucked away with the rest of the elements. That's not what I meant to do. So we had looked at acetic acid. We learned how to name that HC2H3O2. That's acetic acid. And sometimes students want to write C2H4O2. Well, it's the same number of hydrogens, carbons, and oxygens, but we don't usually write an acid this way. And when we talked about nomenclature, I told you that you recognize an acid because it starts with H, right? And so this is just a convention that we always do. Arrhenius definition of a base. A base produces hydroxide ions in solution. So sodium hydroxide is an Arrhenius base. When we put sodium hydroxide into water, this is an ionic compound. It dissolves in water and it separates into sodium ions and hydroxide ions. So we can recognize bases because most metal hydroxides are bases. So KOH, calcium hydroxide. These are ionic compounds containing hydroxide. Not everything that has OH in its formula is a base, though. This guy right here, CH3OH. You might see the OH and say, hey, oh, there's a base. I see the OH. But that's not a base, it's an alcohol. It's a covalent compound, and it doesn't release hydroxide ions. So in this class, Arrhenius bases are metal hydroxides. So acids release hydrogen ions, bases release hydroxide ions. What happens when a hydrogen ion and a hydroxide ion run into each other? They make water. They neutralize each other. So this is the net ionic equation for the reaction between an acid and a base. And the Arrhenius definition explains this for a lot of acids and bases. But there are substances like ammonia that do produce hydroxide ions in solution, even though they don't have hydroxide in their formula. And so the Arrhenius definition doesn't work for that. It also doesn't work for non-aqueous solvents, which we don't need to worry about too much in this class. But in organic chemistry, they use a lot of non-aqueous solvents, and the Arrhenius definition just doesn't help at all. And so that's why other definitions were needed. Another definition is the Brønsted-Lowry definition. This is named for two scientists. And this does not contradict the Arrhenius definition, but it expands the things that get classified as acids and bases. So here an acid is a proton donor. A base is a proton acceptor. This is focusing on the transfer of hydrogen ions instead of focusing on the hydrogen ion and the hydroxide ion just being released into solution. Because what is a hydrogen ion? It's a proton. So an acid being a proton donor, when you stick an acid in water, it donates a proton to the water. I think I've got some more coming up here. Let's see, yeah. So here, when we put hydrochloric acid, HCl, into water, it donates this proton to a water molecule, which is produces this hydronium ion, and then the chloride is hanging around.
But wouldn't that definition make water a base and water is neutral?
Very good observation. It does make water a base. And what we'll find is that water can act as an acid or as a base. So there's a lot of things that we don't think of as acids and bases, but actually they are when we look at the Brønsted-Lowry definition. So the water is a base in this situation because it accepts the hydrogen ion from the acid. Brønsted-Lowry definition explains why ammonia acts as a base. When you put ammonia in water, hydroxide ions are produced, but NH3 doesn't have an oxygen in it. How can it produce hydroxide ions? It does so by accepting a hydrogen ion from the water molecule. A Brønsted-Lowry base is a proton acceptor. So the ammonia accepts a proton from water. The water is acting as the acid here. And after water donates a proton to the ammonia, you get ammonium ion and hydroxide ion. So you put ammonia in water, it does produce hydroxide ions. It is a base. So we always have proton acceptors and proton donors working together. So the acid is like the parent with the baby, and the base is the babysitter. You want to go out for the night. You know, babies are a lot more trouble than dogs, for those of you who don't have children yet. The dog you can leave in the backyard. You can't leave babies in the backyard. You'll get in trouble. Eventually you will. So you have to hand that baby off to someone, right? So the base is the babysitter who says, oh yeah, I'll take care of your baby for a while. I'll take the hydrogen ion and hold on to it. It's too small to be out by itself. So here HCl is the acid. It's donating a proton to the water. We add H plus to water, we get H3O plus. We subtract H plus from HCl and we're left at Cl minus. So this is the acid, that's the base. With ammonia in water, the ammonia is the base, that's the babysitter, it accepts the proton, and water now is the acid and is giving a hydrogen ion to the ammonia. That forms ammonium, and when water has lost a hydrogen ion, it's hydroxide ion. And we have a name for this, it's called amphoteric. An amphoteric substance can act as an acid or as a base, just like an amphibian can live in the water or on the land, right? So water is amphoteric. Water's cool stuff. Okay, let's look at this bottom equation. We have ammonia plus water is in equilibrium with ammonium plus hydroxide ion. What I'm going to do in the next slide is I'm going to take this equation and write it backwards. So now we've got ammonium ion plus hydroxide ion giving ammonia and water. And see, this is another benefit of doing chapter 15 first. We've already talked about this dynamic equilibrium, so we understand that the reaction can proceed in the forward direction and the reverse direction at the same time. It's like people moving from Narnia to Middle Earth while other people are moving from Middle Earth to Narnia. It may not seem like it accomplishes much, but it's what happens, right? People move around. Whenever I go to LA, I'm like, why do all these people need to go somewhere right now? There's so many people going that way, and there's just as many people going that way, and if we just all stayed in one place, it'd be so much easier. But the molecules are reacting, and they're going back and forth. If we look at it in this direction, ammonium can donate a hydrogen ion to the hydroxide. When it donates, it's an acid. Hydroxide ion can accept a hydrogen ion. That's what a base does. The base babysits. Says, well, yeah, I'll take that hydrogen ion off your hands. And then we're back with ammonia and water. Now, ammonium is acting as the acid, hydroxide ion is acting as the base. And with a child, you know, the parent hands off the baby to a babysitter. Does the babysitter take the child and keep him for the rest of his life? Hopefully not, right? They're going to give it back. And so it's this back and forth, back and forth. So we refer to ammonium and ammonia as a conjugate acid-base pair. Because this can be a base, this acts as the base, but after it's accepted a proton, now it can act as an acid. So a conjugate acid-base pair is two substances related to each other by the transfer of a proton. The difference between NH4 plus and NH3 is H plus. No, okay. I thought I had it written out, but I'll have to write it out myself. So how do we get, just looking at the formulas, that's not a very good plus. There we go. They both have a nitrogen. This one has 3 hydrogens. This one has 4 hydrogens. You see, if I take a hydrogen ion off of that, let's see, minus an H plus, that's going to give me this, right? Or I could think of it this way, NH3, and if I add an H plus to that, now I've got 4 hydrogens and I've got a positive charge. The difference between ammonium and ammonia is a hydrogen ion. So those two things are a conjugate acid-base pair. Any two substances related to each other by the transfer of a proton, a hydrogen ion, can be considered a conjugate acid-base pair. Oh, yeah, here's what I was looking for. So the ammonia, if you add an H plus, that's this guy up here getting stuck on, you get NH4 plus. This can act as an acid, this can act as a base. Water, H2O and OH minus are a conjugate acid-base pair. If we take a hydrogen ion off of water, it becomes hydroxide ion. If we add a hydrogen ion to hydroxide ion, it becomes a water molecule. These two things differ by a hydrogen ion. So in this reaction between ammonia and water, ammonia is acting as the base, water is acting as the acid. After the reaction, the ammonia has become ammonium, which is the conjugate acid of ammonia. And hydroxide is the conjugate base of water. When this reaction goes in reverse, ammonium is the acid and hydroxide is the base. Any questions? It's kind of a lot to get your mind around. I'll take that for stunned silence. Okay. This is something you need to be able to do on an exam. It would just be on the final, though. Identify what's the acid, what's the base, what's the conjugate acid, and which one is the conjugate base. Now, I told you there's 2 definitions, Arrhenius and Brønsted-Lowry. I am not going to quiz you on which definition has which name. Okay, I don't see the point in that. So here I'm saying Brønsted-Lowry, but just which is the acid, which is the base. So let's look at this first reaction. So we look at this and it's like, well, that's not a metal hydroxide, but it doesn't start with H either, so we're not sure what's going on with that. And here we've got water, and we should just know in the back of our minds, water can act as an acid or a base, very versatile. Let's look what happens to this molecule. C5H5N becomes C5H5NH+. This has a hydrogen ion added to that. Do you see that? We're just, this is like those things they did on Sesame Street. Or those little puzzles on the Go-Gurt. What's the difference between these two pictures, right? What's the difference between this and that? Well, this has an extra H+. So that means that this guy took the baby. Oh, I'll babysit for you. And here is that guy holding the baby. So then it was acting as a base here, right? So here, this is the base. And when the base accepts the baby, accepts the hydrogen ion, now it has the potential to donate the hydrogen ion either back to the person that gave it to him or to someone else something that can donate a hydrogen ion is an acid. So this guy is the conjugate acid. So the reactants we're going to label as acid and base. The products get labeled as conjugate acid and conjugate base. So if this is a base, that means water has to be acting as an acid. You have to have one of each. You can't have two acids reacting or two bases reacting. They'll mix, but they won't react. So this has to be the acid. And what do acids do? Acids donate protons. So this one, we're expecting to lose a hydrogen ion. And this is what it becomes, and yes, it's lost its hydrogen ion. So then this is the conjugate base. Does that make any sense? It's like playing some weird game. I know it is. So down here we've got HNO3 and H2O. Look what happens to this guy. I mean, I think everybody can identify that this one and that one are related, and this one and that one are related. And the order could be switched, but this one has nitrogen and oxygen, and this one has nitrogen and oxygen. So what happened to this guy to make that guy? It lost a hydrogen. It donated a hydrogen. Acids donate hydrogens. Bases are babysitters. They accept the baby. Bases accept hydrogen ions or protons. So this is the acid. Once you identify one of them, then the other has to be the other. There's one acid and one base, so this is the base. What this one turns into, it was the acid, it turns into the conjugate base. So that's the conjugate base. And then what's the H3O plus? The conjugate acid. Any questions? Practice this a couple times on the homework and it should be okay.